Welcome to Conceptual Physics at Delaware Tech, Chapter 7, Energy. So in this unit, we're going to cover definitions of energy. We'll talk about types of energy and some of their properties. We'll talk about work. Work is a specific form of energy. We'll also talk about power. Power is energy per time. Then we're going to come back to energy again, and we'll talk about the two main categories of what we call mechanical energy. Those are potential energy and kinetic energy. Then we'll talk about how work relates to kinetic energy. It's called the work energy theorem. And then we'll talk about conservation of energy, how energy is never lost. It's just converted to one form or another. We'll talk about how basic machines work and the efficiency of machines. And then we'll cover recycled energy, energy for life, and sources of energy, some modern sources of energy. So the universe is composed of both matter and energy. And yes, if you ask Einstein, that matter and energy are actually different versions of the same thing, but we're going to keep them separate for just now. There are kinds where we have to think of them as the same stuff. But energy is the capacity to do work. So all forms of energy can be interconverted. All forms can be interconverted. So there are many kinds of forms of energy. There's work energy, thermal energy, that's heat, mechanical energy, which is movement, or potential for movement, that can come in forms of kinetic and potential energy. Kinetic energy refers to any energy that involves movement, and potential energy refers to any energy that involves a special position of some object or particle. We have chemical energy from chemical reactions. We have nuclear energy from nuclear reactions. We have electromagnetic energy. This is energy between either charged particles for the electro part, the electric part, electrostatic part, or between magnetic poles. That's the magnetic part of it. Movement of electrons in wires that can produce electric energy. We have gravitational energy due to our position or any object's position relative to another body that has gravity. So energy is a mover of substances, okay? It can be used to move materials, move matter. And energy is both a thing and a process. So it's observed more easily when it's transferred or transformed. So when energy is doing something, that's when we can actually measure it the easiest. It's conserved in all reactions. In other words, there's always the same amount of energy before and after. It just might be in very different forms. Even in nuclear reactions, where mass of particles can be converted to energy, the equivalent amount of mass using E equals mc squared will tell us exactly how much energy it is the equivalent of. So while it might be converted from mass to energy or energy to mass, we don't lose any actual stuff. So energy is a property of a system that enables it to do work. All forms of energy can be converted to heat, and heat is another form of energy. The sun's nuclear reactions produce electromagnetic radiation. Okay, so this is the light, basically in all its forms, anywhere from radio waves to visible light to gamma rays. Those are the electromagnetic radiation, the EM spectrum, that warms the earth. An object falling on the ground warms the ground. When it hits the ground, that energy is ultimately converted to heat. At first, it doesn't have any kinetic energy because it's not moving. It has potential energy because it's sitting in a position that wants to be different because gravity's pulling it down, so that has potential energy. We'll talk a little bit about more of that later. And as it moves, it gains kinetic energy, it loses potential energy, and then right before it hits, it has maximal kinetic energy, and then it hits and it transfers all that energy to the ground or to the air, usually in the form of heat or maybe of deformation of the ground. Electricity can heat up the wires as well as the light bulbs to produce light, as well as driving the energy for appliances. Matter, on the other hand, these are substances we can typically see, feel, or smell, or detect in some way. These are actual particles that occupy space and have mass. And in fact, that's actually the technical definition of matter, anything that occupies space and has mass. and that includes all solids, all liquids, all gases, all plasma. Plasma is ionized gas. Atoms, most subatomic particles, with the exception of things like photons, which are particles of light. That's considered energy. That's the EM spectrum that I just mentioned. These particles all occupy space and have mass. So work is a form of energy. Heat is a form of energy. There are a lot of forms of energy, but work energy involves the movement of objects. And in physics, work is considered the ability to move an object using a force and moving that object by a certain distance. So work, we're using W for work, equals force times the distance, D. So two things have to occur whenever work is done. Work to a physicist. A force has to be applied and the object has to actually move because of that force. If the object doesn't move, it doesn't matter how much force you apply. Distance would be zero, so zero times the force is still zero work. So you need both. So if you push against a stationary brick wall for several minutes, you do no work, A, on the wall, B, at all, C, both, D, none. Well, you're doing no work on the wall. The wall's not moving, so you didn't do any work on the wall. Work, as I mentioned to a physicist, is force times distance. W equals FD. So that means work is proportional to the force that's used, and it's proportional to the distance the object is moved. Both are proportionality. If for some reason you were keeping the amount of work energy constant, the force and distance would be inversely related to one another because they're multiplied by each other on the same side of the formula. In other words, if the work energy is constant, the only thing you can vary is force and distance. If force goes up, the amount of distance that you can move the force goes down. If the amount of force goes down, you can push it a greater distance for the same amount of work. Likewise, if you want to push more distance, you have to use less force, or less distance, more force to get the same amount of work energy. So those are inversely proportional. So if the wall doesn't move, no work has been done on it, on the wall. So why don't we select B or C? Because even though the wall didn't move, no work was done on the wall, you did move your muscles to try to push the wall. At some point you moved your muscles, so work may have been done on your muscles, just not on the wall. So let's take a look at these proportionalities between work and force and work and distance. So if you have twice as much work will be done if you're lifting two loads to a certain height rather than lifting one load to a certain height. Well, remember, what does that mean? That means you have twice the weight that you're lifting. And weight, what is weight? Weight is equal to the amount of force needed to lift that weight. So weight and force, remember, weight is a type of force. So if something weighs 500 newtons, 500 newtons is the force necessary to lift that object. So if we've got two of those weights, we're going to have double the force we need to use to lift the weights, and therefore we'll have double the work. 2 times the weight means 2 times the force, means 2 times the work. If we instead keep the same amount of force, in other words, the same amount of weight we're lifting, but we're lifting it up 2 stories instead of 1 story, that's twice the height, twice the distance we're lifting it up against gravity. And therefore, we will also double the work. We're doubling D, we're doubling the distance. It just happens the distance is also the height in this case. It's a vertical distance. And therefore, the work will be doubled in the process. And a weightlifter has to deal with this. Weightlifter is raising up a barbell from the floor. They're doing work on the barbell. The barbell has a certain weight. It has a certain distance to lift it up above their head. The weight, the force of the weight times the distance, the height they're lifting it, is the work that's necessary. And work has a lot of different units. Remember, energy energy is the catch-all term for all these different types of energies, including work, including heat. So the unit for energy would be, we're multiplying force times distance. So force would be in newtons, weight is also in newtons, times distance in meters. So it's a Newton meter. And that would be the unit we would use. But Newton meter has a special name that's been given to it called the joule. So a Newton meter is a joule. Joule is the unit of energy in the SI and metric system. Since the meter since the Newton is composed of other units, when you put them all together and when you break the pieces down, a joule, which is equal to a Newton meter, is also equal to a kilogram meter squared per second squared. But why am I even showing you this? Why I'm showing you this is this. If you have a weight in newtons and a distance in meters, when you multiply them together, you'll get joules for your unit of energy. And that's the easiest way to deal with it at this point. But there are other units of energy. There's the foot-pound. You may have heard of this. A foot is a unit of length. That's your distance. A pound is a unit of weight or force. So that's your F. So a foot-pound is the imperial version of a joule. But there are a lot of other energy units. There's a calorie, what we call the small c calorie, the big C calorie, which is actually 1,000 small c calories. And the big C calorie is the calorie that in the United States you read on the packages of any food. So when you're reading about how many calories your food has, it's actually 1,000 times more in the real calories, the little c calories. So if it says, oh, this has 50 calories, it's actually, to a scientist, 50,000 little c calories. A big C calorie is the same thing as a kilocalorie of the regular calorie. But there's also other metric-like units. I told you about the CGS system, which is like the metric system. The erg is the unit of energy for that. But we're not going to be using most of these units here. We're going to stick primarily to the joule or the foot-pound. A little quote here from Richard Feynman, the famous Nobel Prize-winning physicist. He said, "For those who want proof the physicists are human, the proof is the idiocy of all the different units which they use for measuring energy." And these aren't all the units that they use. There are a lot more. All right, so work is done in lifting a barbell. How much work is done in lifting a barbell that is twice as heavy up the same distance? Well, we're doubling the weight. That means you're doubling the force needed to lift the weight, but it's the same D. So you're doubling F, you're keeping D the same. What will happen to the work? Twice as much, half as much, the same, depends on the speed of the lift. Well, I think you probably figured it out. It's twice as much. Work to a physicist is force times distance. Weight is the force needed to lift the weight. So if you double the weight, you're going to double the force. 2F instead of F times D will give you 2 times the original FD, or 2 times the old amount of work. And therefore, you're doubling the weight, you're doubling the force. That means you're doubling the work. Work is proportional to force. Whatever you do to force, whatever you do to the weight you're lifting, that's what's going to happen to the work. If I tripled the weight, I triple the work for the same distance. If I cut down the weight tenfold, I will cut down the work tenfold. You do work when pushing a cart with a constant force. If you push a cart twice as far, okay, you're doubling D now, then the work you do is A, less than twice as much, B, twice as much, C, more than twice as much, D, 0. So you've doubled the distance. Well, we already know work is proportional to distance. So if you have that formula and you suddenly double the distance, you're going to double the work. Work is proportional to distance. 2 times the distance, or 2 times the height if you're lifting it up, you'll get 2 times as much. You'll need 2 times as much energy to do that job. Now, power is not the same as energy. Power is a measure of how fast that work is done. In other words, power is work divided by time. It's the work per time. So when somebody asks you what the power is, you have to take the energy of the job, the work, and divide it by time. So as a result, the units of power are going to be some work unit, like joules, divided by some time unit, like seconds. We actually call that unit a watt, by the way. I know you've heard that. Okay, so examples. A worker uses more power running up the stairs than slowly walking up the stairs. Now, think about this. They still need exactly the same amount of energy. They're still lifting their mass, their body, their weight, that's a force, up a flight of stairs. The distance up is exactly the same. The weight, the force is exactly the same. So if your F is the same and your D is the same, your work is going to be the same. The difference is one of them took less time than the other. And the less time you take, the more power you need. So if we go back to this formula, you will see that power is proportional to work. They're both in the numerator on both sides. But power is inversely proportional to time. If you have more power, you can do the job in less time. If you take more time to do the job, it will require less power. All right, power is work per time. Power and time are inversely proportional. Power and work are directly proportional. All right, so here's another example. An engine with twice the power can do twice the work of the less powerful engine in the same amount of time. So here's a situation where the power is increased, the work is increased because they're proportional, but you're keeping the same amount of time. And this is just saying that power and work are proportional. You double one, you can double the other. If I have twice the power, I can do twice the work in the same T. Another proportionality, an engine with twice the power, so we double the power, can do the same amount of work, so work is constant, as a less powerful engine in half the time. Remember I said power and time are inversely proportional. Time is in the denominator on the right side of the equation, power is in the numerator, so they will have opposite effects. You double the power, you cut the time in half. If I cut the power down tenfold, it would take me 10 times as longer increased time to do the job. They are inversely proportional. An engine with twice the power can change one form of energy into another at twice the rate. So again, twice the power just means twice the rate. Power is a rate of work per time. So going back to the units, power is measured in joules per second, what we call a watt after James Watt, the developer of the steam engine. So joules divided by second, remember energy divided by time is power. So joules, the unit of energy, divided by second, the unit of time, will give you watts, the unit of power. So unit of power is in energy units divided by time units. And so it's joule, a watt is a joule per second. And if you break that down into the fundamental units, it works out to a kilogram meter squared per second cubed, but you don't have to worry about that. I'm just showing it for completeness sake. 1,000 watts is what we call a kilowatt. Anytime you see kilo in front of a unit, it means it's 1,000 of that unit. In case you're having trouble remembering that, most of you have heard people say, oh, how much did they make last year? And they said they made 50K. Well, that K stands for the prefix kilo. So when somebody's saying I made 50K last year, they literally mean I made 50 kilo dollars. I made $50,000. Kilo is just an ancient word for 1,000. So 1 kilowatt is 1,000 watts. And we would abbreviate a kilowatt. A watt is abbreviated with a capital W. I know that gets confusing because that unit for watt looks like the same property of work, that abbreviation, and it's the same capital W that's used for weight. So it gets really confusing. I didn't make up these abbreviations. I apologize for that, but you just have to make sure you understand the context of when these are used. So a kilowatt is abbreviated as lowercase k, that's the kilo, and a capital W for watt. So a job can be done quickly, slowly, or quickly. Both may require the same amount of work, but will definitely require different amounts of A, energy, E, B, momentum, P, lowercase p, C, power, uppercase P, D, impulse, I. Well, let's think about this. First of all, the question says the same amount of work. So we know right away that they definitely have the same energy. Work is the form of energy involved here. When a job is being done, that energy to do the job is called the work energy. All right, so the work can be done slowly or quickly. Well, that's your key to this question. Slowly means a large time. Quickly means a short time. Well, when you do work with a long time, work divided by a large time will give you a small power. And work divided by a short time, when it's done quickly, will give you a high power. So power is the answer we're going to go with here. But let's think about some of the other parts of this. Power, we know, is inversely proportional to the time. Low time, high power. High time, low power, if we're keeping the work the same. As I mentioned, work is a form of energy. But momentum and impulse may also be related here, because we're doing the job either quickly or slowly. So that object we're pushing with a certain force over a certain distance is going to move either quickly or it's going to move slowly. So yes, there's going to be a change in momentum as we're doing it. We're moving it with a certain momentum. Eventually we'll stop, but we're moving it with a certain momentum, but the momentum may be very different when they're moved quickly or slowly, or they might be the same. It depends on how this job is done. So you can't necessarily say anything about the momentum or the impulse in this case. That's a bit tricky. Mechanical energy. Now, mechanical energy is kind of a catch-all term. Mechanical energy is related to machines, as the word mechanical would imply, but mechanics is kind of a physics term that means related to physical forces. So mechanical energy is essentially the sum of two very specific categories of energy. And one is based on where that object is in space or what it's next to, and relative to other objects or other forces. That's a positional energy, and we'll talk about that in a second. And the other is related to how much velocity that object has and how much mass it has, what's referred to as the kinetics, the motion of the object. And you have these two forms of energy, or it's the sum of both of them. And a lot of times an object will have both of these. So the two kinds, the one that depends on position is called potential energy. So position, potential. That should be easy to remember. We'll abbreviate it PE. In a lot of more technical physics books, they'll use U as the abbreviation, but we won't be doing that. Kinetic energy, I'll abbreviate as KE. It's a form. These are both forms of energy. They're really categories of energy. So kinetic energy is energy that's involved anytime an object is moving. We talked briefly about this before. It's calculated as 1/2 the mass times the velocity squared. So you need to have mass and you need to have velocity to have kinetic energy. Potential energy is dependent on where that matter is sitting, where it is relative to other objects, to other forces that are on that object. So potential energy is stored energy. It has the potential for doing work. It's energy that's usually due to a special position of an object or a particle, usually relative to some place that's generating a force. An electric force, a positive or negative charge, a magnetic force, a north or south pole. It could be relative to a source of gravity like the Earth or the Moon or the Sun or some other heavenly body. All of these can create potential energy, which basically means the object will move if you let it go. It's not moving right now, so it has the potential to move, the potential to do work. That's potential energy. Now, objects can have both potential and kinetic energy, absolutely, but right now we're going to focus on potential here. So here are some examples of potential energy. A stretch bow has stored energy that can do work on an arrow. So you pull back the bow, it's not moving yet, but there's energy stored in here. You had to put work energy in just to get the bow there. That's how we know there's energy there, because you did work, and the work energy had to go somewhere. It went into being the potential energy of holding that bowstring back. Once you let it go, the bowstring flies, and now it's kinetic energy. A stretched rubber band of a slingshot has stored energy. Same phenomena. You're pulling the sling of the slingshot back. You had to do work to get it to that place where it's kind of unstable. That's the potential energy built into the sling. As soon as you let it go, the potential energy is turned into kinetic energy. It moves. Third example, a compressed or even extended spring. So you can take a spring and either hold it squeezed tight, which it doesn't want to do, or you can take the spring and stretch it out, which it doesn't want to do. It wants to come back. And anytime you deviate a spring from that natural center position by either compressing it or expanding it, extending it, you are adding potential energy to that spring. You had to do work to do that, but once you've done the work, it now has the potential energy is now stored in the spring that is not in its natural position. The last example, an object on the ledge of a building has the potential for falling back to Earth and releasing its energy into the ground. We call this gravitational potential energy. A lot of different types of energy have both potential energy versions and kinetic energy versions. The gravitational energy, we're mostly concerned with the potential energy. So if you're holding an object above the ground, it doesn't want to be above the ground. The second you let it go, it's going to release. So you had to do work to get it to that height. And now that energy is stored in the object that's at that unstable position. Of course, when you let it go, the potential energy gradually is lost because it's going down lower. The lower it is, the less potential energy. But at the same time, it's getting faster and faster. So the kinetic energy is increasing. But the amount of energy it has at any one moment is total energy is the same. So potential energy due to an elevated position of an object above the ground, that's called the gravitational potential energy. The energy due to holding it against gravity. The work you had to do to get it up here. In other words, you had to fight the weight, the force, which is equal to the weight, times the height, which is your distance, your vertical distance. So examples of that are holding up water in an elevated reservoir. Water that's up top is at high potential energy. The raised ram of a pile driver. If you've ever seen construction companies that are just starting to build a building, they're putting these giant concrete piles in the ground as supports for the foundation of the building, and those things have to be rammed into the ground. So by holding these incredibly heavy weights up high, you give them enough potential energy so that when you slam them down, it's easy to pierce the earth. A rock slide hitting a car windshield. The rocks are held up high. The potential energy is there before they start falling. As they fall, that's turned into kinetic energy. Their potential energy gets lower and lower. Their kinetic energy gets higher and higher as they get faster and faster. They hit the windshield, and all that energy is transferred to the windshield. So gravitational potential energy, again, is a form of work energy. It takes work to get it to that potential energy. So work, remember, is the force times the distance. It's, in this case, it's the weight, that's your force, times the distance, which is your vertical height, because we're moving things up against the force of gravity from Earth. So force times distance, which is your usual work formula, becomes weight times height. And weight times height, remember, weight is m times g, mass times the acceleration due to gravity. By substituting mg for weight was your force originally, you end up with a new formula for potential energy, the gravitational potential energy, which is mass times gravity, that's your weight, times height, that's your distance. So it's the same formula in a slightly different form. Potential energy is mgh, mass, gravity, height. That's what you're going to multiply. Does a car hoisted up for repairs in a service station have increased potential energy relative to the floor? A, yes. B, no. C, sometimes. D, not enough information to tell. Well, we already know that gravitational potential energy is dependent on three things. the acceleration due to gravity. So on a different planet or a moon, it would be different. The amount of mass, well, we haven't changed the amount of mass. We're just raising the same car from a low height to a high height. And the height, well, the height is one of the things that potential energy is dependent on. Potential energy is proportional to the height you raise the mass. It is proportional to the mass that you're raising, and it's proportional to the gravity of whatever heavenly body you happen to be sitting on, lifting an object from the surface of. So it's yes. PE equals mgh. That's the same thing as force times distance. It's just the distance is height, the up distance. So if height were increased, PE is increased. They are directly proportional. Increasing the mass or increasing the weight would also increase the PE. Remember, the weight is really just the force. Okay, so here's another example of potential energy in a comparison. We have a potential energy of 10 Newton balls. 10 Newton is about 1/10 of that is 1 kilogram. That's how you figure it out real quickly. 1 kilogram balls, 10 Newtons, is the same in all three cases. So if you look at this, every one of these towers, no matter what the shape is, no matter what the path is for the ball to come down, they're all 3 meters high. So the first one, it's just a fall of 3 meters. And the second one, it's rolling down 5 meters, but it's moving down physically, vertically down 3 meters. And in the last case, it's doing it in steps, dropping, moving across, dropping, moving across, dropping, but a total drop of 3 meters. So you only care about the vertical height. You don't care about how far it travels. You don't care about the path it takes. It's just how high it is above the ground, relative to the ground, if that's what you're interested in. So potential energy is usually relative to the potential energy of the ground, unless stated otherwise. So all three of these have the same exact energy. It's going to be the mass times gravity, which they've already given you as 10 newtons. That's the weight, the force, times 3 meters. So in each of these cases, it's 10 newtons times 3 meters, or 33 newton meters, also known as, 30 newton meters, also known as 30 joules. That's the unit of energy. It's the unit of potential energy, kinetic energy, work, heat, whatever type of energy you want. Use joules for the metric system. All right, so kinetic energy is the energy of motion. So this is separate from potential energy. Kinetic energy depends on the mass of the object and the square of its speed, the square of its velocity. It is proportional to the mass and proportional to the square of the velocity. The formula also includes a constant in it, 1/2. So the formula is kinetic energy equals 1/2 times mass times speed squared, technically velocity squared. But remember, you're multiplying it by speed and then multiplying it by speed again. So what that means is if you increase the speed a certain amount, you have to square how much you increased it to figure out how it affects the kinetic energy. So kinetic energy, by looking at this formula, you see kinetic energy is directly proportional to mass. Double the mass, double the kinetic energy. Increase the mass tenfold, you'll increase the kinetic energy tenfold. Decrease the mass tenfold, you'll decrease the kinetic energy tenfold. Velocity, however, is a squared term. So kinetic energy is directly proportional to the square of the velocity, the speed. And in most cases, we'll just look at speed. So that means if I double the speed, that means I'm increasing the speed twofold. If I'm increasing the speed twofold and the velocity term is in there, speed times speed, it's twofold times twofold, or 2 squared. So doubling the velocity will quadruple the kinetic energy. If I increase the velocity tenfold, I will increase the kinetic energy tenfold times tenfold, or tenfold squared, which is 100-fold. Likewise, if I cut the velocity in half, that means I'm decreasing it twofold. The kinetic energy will decrease 4-fold. If I decrease the velocity 3-fold, I will decrease the kinetic energy 3 times 3 squared, 9-fold. So you have to square whatever happens to the velocity to figure out what happens to the kinetic energy. So, must a car with momentum have kinetic energy? If a car has momentum, does it also have kinetic energy? A, yes, due to motion alone. B, yes, when momentum is not non-accelerated, not accelerated, constant speed. C, yes, because speed is a scalar and velocity is a vector quantity. D, no. I'll let you think about that for a second. Well, it's A. Technically, it's not just the motion, it's the motion and the fact that they have mass. Remember, the formula for momentum, P equals mv, P is dependent on the mass and the velocity. If either one of those mass or velocity is zero, there's no momentum. And the same is true of kinetic energy. Kinetic energy is dependent on only two things, the mass and the velocity, the same two things. If it has momentum, it must have had mass and velocity. If it has mass and velocity, it must have kinetic energy, and all vice versa. So they both depend on mass and energy. Any moving object will have both momentum, because it's moving and has mass, and kinetic energy, because it's moving and has mass. So the facts that velocity and acceleration are vectors and that speed is a scalar is really irrelevant. It's true, but it doesn't have anything to do with this problem. Kinetic energy, work done, and the kinetic energy of a moving object. So now we're going to look at the relationship between work energy and kinetic energy. So one way to think about work, remember, you're taking an object and you're applying a force and you're moving it from one place to another. So work is the energy required to bring that object from rest to a certain speed in order to move it. And work is also the energy required to bring that object to rest. So you have to move it. It has to be moving at some point along the way. So kinetic energy will be involved when you're doing work. So it turns out work is equal to the change in kinetic energy. If you're going from something, some kinetic energy and movement to no movement, the work would be the difference between the two. It would be zero minus the original energy that was in there, initial kinetic energy due to movement. If you're starting from zero speed and you're moving it, it's the other way around. It's the final energy of movement, the kinetic energy of movement, minus the zero initial speed. But it's still closely related to the kinetic energy. So the formula here is that while we know that work is equal to F times D, force times distance, and we know kinetic energy is equal to 1/2 mass times velocity squared, we also know that work is the change in this kinetic energy, which is frequently just the kinetic energy of either the beginning or the end if the other one is zero. And those are the situations we would give you. So in that case, the force times the distance, that's the work, is equal to the change in kinetic energy, the change in the 1/2 mv squared value. But that change in the value will just be the 1/2 mv squared value if either you went from something to zero or from zero to something. The only thing that would have to change is a negative sign, but we're not going to worry about that here. So usually it's frequently simplified to this when you're dealing with going from no speed to some speed or going from some speed to dead stop. It simplifies to this equation. Fd, the work, is equal to the kinetic energy of the time it had kinetic energy. And this is referred to as the work energy theorem. So the gain or reduction of energy is the result of work. In other words, you got a car moving with a certain velocity and it's got a certain mass, so it has a certain kinetic energy. To stop that car, you have to do work to stop it. And that will require a force, and it will take a certain distance to stop the car. Force times distance equals the change in kinetic energy of the car. And you can use this theorem to figure out how far it takes a car to stop if you know how much force you can use to stop the car. So work is the change in kinetic energy. And here's the formula that we gave before. So if you look at this, you can see a number of different proportionality relationships. Since work is equal to the change in kinetic energy, in this case it's just equal to the kinetic energy of the time that it had kinetic energy, W equals 1/2 mv squared, the same as the kinetic energy. That means the work it takes to stop an object is proportional to the mass, but it's also proportional to the square of the velocity. Now that's an interesting point. It means that if you double the velocity of an object, it takes 4 times as much work to stop it. If you have the same amount of force, it's going to take 4 times the distance to stop it. So there are a lot of relationships in here. Force is dependent on velocity squared. Distance is dependent on velocity squared if you keep the force constant. So look at the formula. Anything that's on opposite sides of equal signs, nothing's in a fraction here, so they're all numerators. They're all directly proportional, though for velocity, it's the velocity squared that's proportional to the work or the force or the distance. Whereas mass is directly proportional to the work or the force or the distance in this equation. So this is the situation where you're using double the velocity, and since you square that term, it becomes the double v, the 2v, when you square it becomes 4v squared. If you pull the 4 out, it's 4 times as much energy. Now, you don't have to worry about this formula, just understand that since work energy is proportional to velocity squared, whatever you do to the velocity, whatever fold change up or down you do to the velocity, 3-fold, you need to square it. 9-fold will be what happens to the work. In this case, work is 4 times as much if you double the velocity. So this definitely applies to decreasing speed, reducing speed of an object. So bringing a car to a stop is an important example. Hitting the brakes. The brakes apply a friction force to the tires. And that friction force is the force necessary to stop the tires over a certain distance. So you have that force times the distance, that's the work, to stop a moving car whose energy is the kinetic energy of that car, 1/2 mv squared. So work is done on it, the friction force is the force times the distance it takes to stop. And we all know it always takes your car a certain distance to stop. You can't just stop, quote unquote, on a dime. It might take 10 meters, 100 meters on a slippery road. You have no idea. On a really slippery road, it could take a great distance. And that's why accidents happen in bad weather. So consider a problem that asks for a distance of a fast-moving crate sliding across the factory floor and then coming to a stop. So right away, you should think fast-moving. It's got kinetic energy. It's got momentum too, but this is not about momentum. It's got kinetic energy, and then it's coming to stop. No kinetic energy. Well, that's a change in kinetic energy. You immediately should think, oh, that's the definition of work. That's a definition of work. It's a change in kinetic energy. And work is also equal to force times distance. So you want something that equates those two. It says the most useful equation for solving this is A, F equals ma. That's Newton's second law. B, Ft equals the change in mv. Well, this is the impulse formula. Ft is equal to impulse. Change in mv is the change in momentum. That's also equal to impulse. C is just the formula for kinetic energy. It's part of this, but it's not. It doesn't equate distance. Distance doesn't appear in this formula. It's just the formula for kinetic energy. The last formula is the work energy theorem, the work kinetic energy theorem, really. So it equates work on the left, F times d is work, with the change in kinetic energy, the delta change, in 1/2 mv squared. That's the change in the kinetic energy formula. So it's d in this case. And there we go. So the work energy formula, it's a physicist's favorite starting point for solving many motion-related problems, especially when you're asked to figure out the distance that something takes to stop or to get up to a certain point of kinetic energy. The formula relates work to changes in kinetic energy. Remember, if the kinetic energy isn't changing, remember it's still moving, and we don't call that work in this case. Because it was already moving. You didn't have to add a force to change its energy. It allows you to solve for distance using force, mass, and velocity. So you need a few pieces of information to figure out that distance. Another question. The work done in bringing a moving car to a stop, so we've been talking about that, is the force of the tire friction times the stopping distance. This is work. Work is equal to force times distance. If the initial speed, v, of the car is doubled, the stopping distance is, well, remember the formula. Think about how the distance, d, on one side of the equation is related to v on the other side of the equation. Remember, v is squared on the other side of the equation, so d is proportional to v squared. If you double v, if you double v, you increase v squared by 2 squared, or 4-fold. And as a result, it's none of the above. You are increasing the stopping distance 4-fold because you increase the work 4-fold. You have the same amount of force. So we have this formula for distance. I just moved the force over to the other side. You don't need to know all this. All you need to know is that F is proportional to v squared, D is proportional to v squared, W is proportional to v squared. They're both on opposite sides of the equation, and v squared is on one side and those other letters are on the other. So anything you do to v, you have to square what you did to v to see what you did to D or F or W, work. Okay, any one of those independently. It doesn't work if you're changing all of them. If you're only changing one thing, like the force, or in this case, the distance, you can look at what happens to v squared. That's what will happen to the distance. So as a result, doubling the speed will result in double squared, 2 times 2, to get the effect on the kinetic energy, and therefore the effect on the work, and therefore the effect on the distance. One is related to the other in the chain. So the law of conservation of energy, and this is a very important law in physics. The more correct version of this is the law of conservation of mass energy, because as Einstein taught us, mass and energy are 2 different versions of the same stuff. But we're not going to talk about mass being converted to energy. That happens in nuclear equations, and that's beyond the scope of this course. So energy cannot be destroyed or created. It can be converted to mass, but we're not going to count that. It's a different version of the same stuff. It can't be converted. It can't be destroyed. You can't lose energy. You can change it to a lot of other things, other versions of the energy, other forms of energy, but you can't destroy it, and you can't make it up. It's got to come from somewhere. So energy has to be either transformed. It has to be transformed from one form to another, but the total energy before something happens has to be exactly equal to the sum of all the energies after it happens. It doesn't change. The total energy never changes. That is the conservation of energy law, and this is a very strict law of physics, important one. Let me back up for just a second. I told you before in a previous unit on momentum that in inelastic collisions, the energy is not conserved. It's not conserved within the momentum of the objects hitting each other. It is conserved because it's turned into heat energy. You just don't see that in your calculations of kinetic energy. All right, so an example of conservation of energy. I've actually alluded to this a few times. The energy transformed without net loss or net gain in the operation of a pile driver. So here you're lifting up a giant heavy weight and holding it. So it took work to get it up here. We can calculate the work. It's the weight mg times the height h, right? Mgh is potential energy. Once it's up here, it has a lot of energy. It would love to leave that thing and just fall down. And as it's falling, it lowers its height, so it has less and less potential energy, but at the same time, it's increasing its velocity, so it has more and more kinetic energy. So initially, you have potential energy up here, and you have kinetic energy that's nothing, because it's not moving. As it's falling, it does this. All the energy becomes kinetic energy until right before the moment it hits the ground. And then the second it hits the ground, it can transfer all that energy. Now it's in the form of kinetic by the time right before it hits, and it transfers that energy into pushing the pile into the ground or smashing into just plain ground. And so it's either the moving of the object, in this case is where the energy goes. Some of it might go to heat, making everything warmer over time when it hits it. But the energy is not lost. It's converted from potential gradually to kinetic. So in the middle, there's a little bit of each. And then by the bottom, it's almost all kinetic, and then it hits the pile and transfers all that into movement, so kinetic energy and work on the pile itself. So at the moment before impact, all the energy is in kinetic energy because it's not high up anymore. The height is essentially zero. But the important part here is that until it actually hits, all along this pathway, the sum of the potential and the kinetic energy, which we call mechanical energy, I introduced you to that term before, the sum of these two is going to be constant. It's constant up until the moment you lose it because it was transferred to something else or transferred to heat. So if you looked at any time during the drop, we're not including the very last moment when it hits, at any time in the drop, if you looked at the potential energy based on its height and the kinetic energy based on its speed, you add those together and then look at any other time in the drop and look at its potential energy based on height and its kinetic energy based on speed. You add those together, those two numbers will be the same. Energy is conserved. So the initial potential energy will actually be equal to the final kinetic energy. And the beauty of this is we know what the initial kinetic energy is. It's the original height times mass times gravity, mg times the initial h. And we know the final kinetic energy, it's 1/2 mv squared. Now we might not know what the v is, but we can figure out what the v will be because we know every other number in here. We know what the mass of that block is at the top. We know what gravity acceleration is. We know the height. We can measure the height. So we know all the terms on the left. We know the mass already. That was already included. And you could rearrange this equation and solve for the final velocity. So if you know the height of an object, you could figure out how fast it is right before it hits the ground. After it hits the ground, where does the energy go? Well, it goes into a couple places. It goes into driving the pile into the ground. So it goes into creating a force doing work on the pile. It also will go into heating up the pile, heating up the block, heating up the air around it. A lot of places. So it's a combination of friction, heat, and work. All right, so here's something to consider. Consider a system of a bow and arrow. In drawing the bow, we do work on the system and give it potential. So you're pulling back, you're doing work energy with your arms to pull the bow into a new position of potential energy. That bow doesn't want to be there. It's got a lot of energy stored in this odd shape of the bow that you're holding it back from. When the bowstring is released, most of the potential energy is transferred to the arrow that's on the bow, boom, and that energy is transferred to the arrow. Some of it will stay in the bow because the bow's also moving. Some of it will go there, but most of the energy will be transferred to the arrow and make the arrow move with its mass and its velocity, and you can calculate its kinetic energy. Some of that energy, however, is lost, and it's lost to become heat that's transferred to the bow. Maybe even a little to the arrow, maybe a little to your hands, and maybe a little to the air. So you're always going to lose a little heat. It's never any kind of machine, and a bow and arrow would be a type of machine. Any kind of machine, no machine that man makes is 100% efficient. It's not perfect. It's not going to use all the energy you put in. All the energy will be released, but it's not always in the form of work that you want it to do, which in this case is to shoot that arrow with a certain speed. You'll lose some. Things will warm up. Things will get stressed. That's where some of the energy goes to. Suppose the potential energy of a drawn bow is 50 joules. In other words, you had to put 50 joules to get this thing back here. Okay? And then the kinetic energy of the shot arrow is 40 joules. So that you know the mass of the arrow. You can measure the velocity when it was released. You can calculate the kinetic energy, and you found it was 40 joules. Then which of the following? A, the energy is not conserved. B, 10 joules go to warming the bow. C, 10 joules go to warming the target. D, 10 joules are mysteriously missing. Well, I think we know A is not true. The energy is not conserved. We know energy is always conserved. It's got to go somewhere. So did it go to the bow? Or did it go to the target, or did it go somewhere else mysterious? Well, think about when it goes to the target. That when it goes to the target, it's the energy from the arrow. It's the 40 joules from the arrow that are being transferred to the target. That has nothing to do with the 10 joules that we haven't accounted for yet. So the 10 joules that are lost have to be somewhere between getting this bow back and releasing the arrow. That 10 joules went to the bow, probably in moving the bow and warming the bow up in the process. Now, this might be an exaggeration, but you're not going to get all your 50 joules into the arrow. Some of it's going to be lost to heat, some of it's lost to friction. You're pulling the arrow against the bow. There are all kinds of little ways you can lose heat from friction and moving through the air, et cetera, et cetera. So it's warming the bow. Energy is always conserved, and the total energy of the drawn bow, which includes the poised arrow, is 50 joules. We know that. The arrow gets 40 of the joules, the remaining 10 got to go somewhere else. It hasn't hit the target yet, so it's already lost by the time the arrow is flying with 40 joules of energy. So it's got to be somewhere in near the system of the bow. All right, so similarities between momentum and kinetic energy. Remember, these are two different properties. Momentum is m times v. Kinetic energy is 1/2 m times v squared. They measure different things. Both are properties of moving objects. They absolutely both require mass and speed. Both formulas include a variable for speed, velocity, v, and both include a variable for mass. The difference is momentum is a vector quantity. Therefore, it has to have a direction, and you can cancel momentum by having momentum in the opposite direction. There is negative momentum. When an object bounces, it has negative the momentum it used to have. So that's possible. But kinetic energy, as well as all forms of energy, is a scalar quantity. It's just an amount of energy. All you can do with energy is add more energy or take away energy. You can't cancel it. I mean, you can the total is always the same. But kinetic energy is one of those forms of energy. But the point is, it's a scalar quantity. It can't be canceled. It can be transferred, but it can't be eliminated by some anti-energy or some negative energy. Yes, there are some very high levels of physics where they're discussing negative energy, and that may be a real thing, but that's way outside of the scope of this discussion. So, velocity dependence. Both kinetic energy and momentum depend on velocity. Momentum depends directly on velocity. Momentum is proportional to velocity. P equals mv. P is on one side, v is on the other. Direct proportionality. Kinetic energy depends on the square of the velocity. Ke equals 1/2 mv squared. So kinetic energy is proportional to the square of velocity. For example, an object moving twice the velocity of another with the same mass has twice the momentum. Remember, P equals mv. You double v, you double p. You double the velocity, you double the momentum. But if you double the velocity, the speed, you're quadrupling the speed squared. 2-fold up times 2-fold up is 4-fold increase in kinetic energy. Increasing the velocity 3-fold, we get the 3-fold increase in momentum, but we get a 9-fold increase in kinetic energy. If we increase the velocity 10-fold, we would bump up momentum 10-fold, but we'd bump up kinetic energy 100-fold. Just like if you decreased the velocity 10-fold, you would decrease kinetic energy 100-fold. And this actually becomes important when you're driving your car. A lot of people don't realize this energy is related to velocity squared term, and it becomes extremely important with pedestrians' lives. Most pedestrians will survive a 25 mile per hour hit. Most pedestrians will die with a 35 mile per hour hit. And this is one of the big reasons that residential areas have speed limits of about 20 or 25 miles per hour. Most people will survive that hit. You go higher than that, most people will not survive that hit. There is an enormous increase in energy when you increase your speed just by 10 miles an hour. It seems like a little bit. You're thinking, oh, I'm going from 25 to 35. That's not that big a change. But it sounds like it's, what is that? About 10 miles out of 25 is 40% increase in speed. 40% increase in speed is almost a double increase in kinetic energy that you're hitting a human being with. And this is one of the reasons why we have to be concerned with both this law and the laws of physics, as well as the laws of speed limits. And I'm certainly as guilty as most people are with not following speed limits sometimes, at least in theory, I'll say that for legal purposes. But the fact is, it's amazing how fast energy ramps up with just a little bit of increase in speed. So this is what I just said. Increasing the speed from 25 to 35 miles an hour is almost double the energy that you would impart in an object that you might hit. Machines. Machines are devices for multiplying forces. What does that even mean? And changing the direction of forces. What does that mean? Well, multiplying forces means machines are designed so that if you use some energy that creates a force, the machine can double or triple or quadruple that force. It can multiply it up depending on the design of the machine. Or the machine will just change the direction. So a pulley, a simple pulley where the rope is going up over a wheel, you're pulling down on the pulley and the object is moving up. The object's not being pulled down, the object's moving up. So a simple pulley is just changing the direction. You're not multiplying up your work. The amount of work you're doing with a simple pulley is the same amount of work that it takes to lift that object up. But there are other versions of pulleys that will multiply your force. Complex pulleys where you will pull and the amount of force you put will end up as 2 or 3 or 4 or 8 times the force that the pulley is actually helping you lift up. And we can talk a little bit about that, but we're not going to go in great detail. So machines don't create the energy. Remember, the energy in has to be the energy out. You can't get around that. They can transfer energy from one form to another. They can transfer energy from one location to another. They can't create energy. They can't destroy energy. They can't multiply the work or energy. They can multiply the force. And remember, work is equal to force distance. So by ramping up with the same amount of energy, the same amount of work you do, a machine can make you do more distance to get more distance to increase your energy by using the same force with a bigger distance. And I'll talk about an example of that in a second. So the work energy in has to be the work energy out. The work energy in has to be the work energy out in principle. This is the principle of conservation of energy. If it worked with just work. Now, it doesn't work with just work because something is always lost to heat or friction or something else. But if the work in is equal to the work out on a machine, in theory, remember that work is force times distance. Well, the force input that's put in the machine times the distance input that's put in the machine can equal the work output, which is the force output times the distance output. What does that all mean? Well, that means that you can use some machines to reduce the force by increasing the distance. So if the left side of this is the same as the right side, in theory, the machines aren't perfectly efficient, but if they were, this is the best you could do. You could have machines designed like complex pulleys, inclined planes, ramps, wheels, etc., where by putting in a little more distance with your force, you can get a lot more work energy, you can get a certain amount of work energy, and on the other end of that same amount of work energy can be turned into a small distance change, but a large force output. So you can make the force output gigantic by making the distance output a little, which means you have to move things a long distance with a low force to get a high force that's moving things a little distance. And that's what complex pulleys do. It's also what levers do. So here's a simple machine, one of the classic 6 or 7 simple machines that physics considers the simplest machines. A wheel and axle, a ramp, also called an inclined plane, a lever, a wedge. There are a number of these. The screw. These are all the simple machines. So a lever takes advantage. You have a fulcrum in the middle. That's the pivot in the middle. It's called a fulcrum. And the work energy you do on one side of the lever, the seesaw, is the same as the work energy output on the other side. And because F times D equals F times D on the output, by changing the D, by using a big distance, you can lift a large weight, a large force, but only a little distance. And that's what this means. So levers are great if you have a long enough lever and the pivot, the fulcrum, is close enough to the heavy weight and you've got a long distance to the fulcrum. You can put your force over a long distance and have a big change in lever motion on your side and only a little change in lever motion on the other side. But the work you put in is the same as the work that's coming out. And if W equals W, the work equals W, the work in is the work out. The FD in is the FD out. By making your D big, you can make their F big. But the downside is when you're putting in all that force, you're only lifting it a little bit. But you can lift a really heavy weight that way a little bit. With a little bit of force and a lot of pushing, that's a little bit of F and a lot of D, you can move a lot of F, a little bit of D. Pulleys do the same thing, but in a different way. So this is on the left here is a simple pulley, and the right is a slight variation. It's kind of a close-up of what's going on with this pulley. So pulleys operate with a lever arm, with equal arms. So we think of it, a lever that's essentially bent around a wheel. That's what a pulley is technically. It's a lever that's, instead of a pivotal fulcrum, it's a wheel that's the fulcrum. So the thing is on both sides. You can think of it that way. But just think of the pulley. You've got a rope. There's a constant tension through the rope. And pulleys are great for changing the direction of your force. You're pulling down, the object is being pulled up in this particular pulley example. So here, we're not really changing our force output. We're not multiplying our force in this simple pulley. But there are complex pulleys where you can multiply the force because it goes around many different wheels, and you might have to pull at a great distance to make a heavy weight move a little bit of height. So pulleys can be combined in different ways. You can combine them with the walls and the ceilings, and combinations of pulleys, attached to other pulleys, what's called block and tackle combinations. And here you can start multiplying your force. So the pulley here, which looks really, really awkward, is actually multiplying her force twice. And the reason why it's multiplying the force in this case is twofold. Number one, she has to lift up twice as much rope to get this thing going up a certain height. So because this pulley is designed the way it is, she has to pull 2 meters of rope to get the weight at the bottom lifted up 1 meter. Why? Because there's rope on either side of the pulley, and both of them have to be shortened by 1 meter to get the pulley up 1 meter. So she's lifting this up a meter and this up a meter, and that means she's pulling 2 meters of rope to get the whole wheel of the pulley lifting up a meter. So she has to do double the distance, but she can end up lifting up this object with twice the weight that she'd normally be able to lift. And the other reason is the other half of the weight that she's lifting is actually supported by the ceiling. So she's only doing half the force necessary to lift it up because the ceiling's doing the other half of the force with the tension into the ceiling. So this one multiplies forces. In this case, the force multiplier, what we call the force multiplier, is 2. It's doubling her ability, the force she can put in. She can lift twice as much as she normally would with this, but she has to pull up twice as much rope to get it to lift the one-fold height. So she has to pull up 2 meters of rope to make the weight lift up 1 meter. So as I mentioned, this particular pulley is a 2-fold multiplier because the ceiling's doing half the work. All right, so in an ideal pulley system, a woman lifts a 100-Newton crate by pulling rope downward with a 25-Newton force. Okay, right away you can see that the amount of force she's using is only a quarter of what she's actually able to lift. For every 1 meter length of rope she pulled downward, the crate rises how much? So she had to put in 1 meter. She had to pull 1 meter. And her force multiplier, you can look at this, she's lifting 4 times as much as she's putting the force in. So her multiplier is 4. 100 newtons, what she's actually being able to pull with the machine, but the amount of force she's putting in is only 25 newtons. So 100 newtons divided by 25 newtons is 4-fold. Well, if she's doing 4-fold as much distance, if the output is 4-fold as much, that means the distance that's coming out, the output distance, must be a quarter of the distance. So a quarter of 1 meter is 25 centimeters. 1 meter is 100 centimeters, so a quarter of that is 25 centimeters. And that's because the FD in must be equal to FD out. And if her F is 1/4, if her F out is 4 times as much, her distance out must be 4 times smaller. And this is just the math if you want to put in the actual numbers, but you can do this logically without actually calculating if you're concerned about the algebra. You can see if the force in times the distance in equals the force out times the distance out. If we're interested in the distance out, we solve for that. It's equal to the force in times the distance in divided by the force out. Plugging in all the numbers, we end up with 0.25 meters. 0.25 meters is 25 centimeters, or 1/4 of the length. So efficiency, no machine is perfect. The amount of work you put in is really never exactly the amount of work you get out of a machine. Energy is conserved, but it's frequently lost to things like heat and friction. The percentage of energy put into a machine that is converted into useful work output is the efficiency of that machine. So mathematically, you can put it into a couple different forms. You can either say the useful energy output over the total energy input times 100%, because it's a percentage, is the efficiency. Another way to say that is the work that the machine puts out divided by the energy that was put into the machine times 100% to make it a percent is the efficiency. It's the percent efficiency of that machine. And some machines have very high efficiencies, over 90%. There are other machines that have terrible efficiencies. An incandescent light bulb, less than 10% efficiency. Most of the energy of a regular light bulb, an incandescent light bulb, most of it is lost to heat instead of producing light. But there are other machines that are amazingly efficient. Certain machine is 30% efficient. This means the machine will convert 30% of the energy input to useful work, and 70% of the energy input will be wasted. B, the opposite, 70% will be turned into useful work and 30% will be wasted. C, both. D, neither. Well, it's hard to imagine it could be both because those are completely conflicting statements. Well, the 30% efficiency means 30% of what you put in is what you get out. You have to put in, maybe you put 100 joules in. You get 30 joules coming out. 30% will come out. That is a 30% efficiency. The other 70% doesn't do work. And it's typically lost to heat or friction, maybe even to light in some possible machines. But usually it's heat in the form of friction or some kind of production of heat. Might be radiant heat from things just getting hot. All right, so recycled energy. Reemployment, that's reuse. That's just a fancy term for reuse of energy that would otherwise be wasted. That's recycling. I think you guys all know that. People talk about recycling all the time. Even back as far as the time when Thomas Edison was around, about 100 years ago, he would use heat from his power plant in New York to actually heat neighboring buildings. So he recycled the heat was generated from the power plant that might otherwise have been wasted or was generated by the power plant for producing heat. Power plants typically waste about 30% of their energy to heat. That sounds like a lot. People are always trying to lower the waste, increase the efficiency. But in this case, it's because the buildings are built away from other buildings and other places that could make use of that heat. Well, why does that happen? Well, a lot of it's safety reasons. You want to keep a lot of buildings away from certain parts of power plants, especially the part that's generating the power. It might be less safe. So you want to keep residential buildings or office buildings away from that just in case there's an accident. Energy for life. The human body is a machine. It's actually a collection of many, many, many machines. Our cells feed on carbon-based compounds. We eat food. Our food is made of carbohydrates, which are carbon, hydrogen, and oxygen. That's carbon-based. It's made of proteins. That's carbon, hydrogen, oxygen, nitrogen, sulfur. So that's mostly carbon-based as well. Lipids, that's your fats. Carbon, hydrogen, oxygen predominantly, some phosphorus in that, but a lot of carbon. These are carbon-based compounds that are burned to produce CO2, carbon dioxide, and that energy is released gradually in your body. It's not like setting it on fire where all the heat's released right away. It's captured one step at a time in the body by your enzymes in the body to convert it into chemical forms of energy that are actually forms of chemical potential energy, stored energy for use later in other chemical reactions. There's more energy stored in food than in products after metabolism. That just means that something is wasted along the way, usually in the form of heat. Some parts of your body do that intentionally. The brown fat in your body purposely is inefficient in order to generate heat, so you have heat in your body. Whereas the white fat in your body tends to burn to produce chemical energy, potential energy. So there's conversion to other forms of energy in your body all the time in order to keep you warm, keep you alive, keep your chemical reactions going. And there's always a loss of heat that you may not want to lose, so there's never 100% efficiency in any machine, including the human body or any other living organism. So, sources of energy. Well, our ultimate source in the solar system is the sun. The sun has nuclear reactions that fuse hydrogen together to form helium. It takes 4 hydrogen atoms and makes 1 helium atom, and that is a very hard reaction to get started, but it is a very, very favorable reaction that produces an enormous amount of energy. Most of that energy comes out in the form of heat and ultimately light that we get from the sun. That light is, of course, electromagnetic radiation. That's our EM spectrum that hits the Earth and warms us. Sunlight will evaporate water on Earth. Water rises up, forms clouds, makes rain. Rain flows down into rivers, and the rivers are moving. So now it's turned into kinetic energy. It hits turbines. Turbines have spinning wheels in them, spinning turbines that can produce energy from the movement of the spinning. And so now you take the sunlight, which was originally fusion energy, to electromagnetic energy. The electromagnetic energy warms up the water. The water falls as rain. That's gravitational energy. The gravitational energy turns the water into rivers. The rivers flow. That's kinetic energy. The kinetic energy hits the turbines, spins them, produces electrical energy, and then the water flows back to the sea and repeats the cycle. And we use the electrical energy to do whatever work we want to do, to run whatever appliances we want to do, to run whatever power plants, et cetera, et cetera. Uneven heating of the atmosphere by uneven heating of the atmosphere is what causes wind. So the sun hits one part of the atmosphere with more heat than other parts. Earth is always rotating, so it's always changing. The Earth has a certain geography with mountains and oceans, so those kind of affect the patterns of the air as well as it's flowing over them, and you end up with wind. And that wind can also be used to turn turbines, wind turbines, and you'll get wind-generated power in the form of electricity ultimately. So that's a different way, a different pathway of going from the fusion of the sun to electromagnetic energy to heat to kinetic energy of the air particles to make wind to kinetic energy of the turbine spinning to electrical energy that's produced by the turbine, and then that can be used. Sunlight can be transformed into electricity directly with something called photovoltaic cells, also called solar cells, to produce what we refer to generally as solar power. So these are chips, usually silicon-based, some kind of semiconductor, that when it's hit by light directly causes electrical current to flow, and that can be captured in the form of electrical energy. So you can take the sunlight hitting, it causes the electrons from electrostatic energy to move, and then you end up forming current, and that forms electromagnetic energy that can be used. So sources of energy. The sun is our ultimate source of energy for most of what we do on the planet. Photovoltaic cells can be put on rooftops. These are the solar cells on rooftops to capture energy. This is not the passive solar collections where you just have water up there and the water's heated by the sun and that can be used. That's a passive system. This is more of an active system where you're literally directly generating electricity from the sunlight hitting it. So the Earth actually receives only 1/1000th of all the energy the sun puts out. Remember, the sun is putting out in all directions, and the Earth is revolving around the sun in one pathway and is a small ball compared to the sun. So what the sun puts out in all directions, the Earth only captures 1/100000th of that hits the planet. But the sun's energy that does hit the Earth can provide enough energy for all of humanity's annual use every year. If you were able to collect all the sunlight that hits the Earth in 1 hour and turn that into energy, electrical useful energy, that would be enough. 1 hour collection would be enough to power the entire planet for an entire year. Because we only use less than 0.01%. That's less than 1/10,000th of the sunlight that hits the Earth. That's all we'd need to power all of human needs. Something to think about. Fuel cells. This is another form of energy. So what I've shown here is the reverse of a fuel cell. This is not a fuel cell. This is the opposite of a fuel cell. This is a water electrolysis cell. So it's basically a battery. And batteries are useful stored energy that can be used to drive chemical reactions in the opposite direction that they'd want to go normally. And they provide the energy to make a reaction go in the opposite direction. And in this case, the reaction they do, if you take a battery and have the electrodes coming off with the wires and you put them in water, water is H2O, 2 hydrogen atoms attached to 1 oxygen atom. If you put these wires in, one of these will be positively charged wire and one will be negatively charged. And if you give it even a few seconds, you'll start seeing bubbles form on one electrode and bubbles form on the other. And one of these electrodes will be forming hydrogen gas from the water, H2 gas from the H2O, and the other will be forming oxygen gas from the water, O2. So you will actually be splitting the water into hydrogen gas and oxygen gas, and those are the two sets of bubbles coming out of here. And we know that because if you took a match and put it over top of this, they'd burst into a quick flame and make water vapor in the process. That's a very, very favorable reaction. So what a fuel cell does is the opposite reaction, the really favorable reaction. If you have a source of hydrogen gas, so you get hydrogen gas, you compress it in the presence of atmospheric oxygen gas. So you're mixing 2 parts hydrogen gas with 1 part oxygen gas, squeezing them together and letting them together, you can actually generate water again, because that's very favorable and produces a lot of energy. And if you do this in a fuel cell, that energy can be transferred back to the electrodes and actually create essentially what is a battery. So it's the exact opposite reaction using something similar in this diagram, but a little bit different design. So now you're taking hydrogen gas and oxygen gas and remaking the water, which is super favorable, and that energy is captured in the form of electrical energy. That is what a fuel cell is. So this energy is super favorable. It will charge up the fuel cell, generate an electrical current that can be used later to power some other devices. So they can power, in theory, they have been used to power zero emission vehicles. These are the so-called hydrogen cars, the cars that burn hydrogen gas. That's the way they do it. And they don't produce any carbon dioxide, so there's no CO2 emissions to warm up the atmosphere. Now there might be a little CO2 production in making the original hydrogen gas in a factory somewhere. Some work had to be done, maybe something had to be burnt to make CO2 gas, but ultimately you'll make a lot less CO2 in this whole overall process, so it's better for the environment. The problem is hydrogen gas is very explosive with oxygen in the atmosphere, so new methods have been developed so that it's not just free hydrogen gas. It's usually hydrogen gas that's mixed in almost like a sponge of metal that the gas fits in the holes of, and it protects the gas from being explosive. And that's one of the waves of the future. But ultimately, our source of energy will be hydrogen gas that people can get from water by doing electrolysis first, getting hydrogen gas, and then using that to basically run out various appliances or cars or any other devices, in theory. So another form of energy that we're all familiar with, nuclear energy. And at present, there are two basic kinds of nuclear energy: fusion energy and fission energy. Fission means a big atom is fizzed apart. It's broken apart. So we use giant atoms like uranium and plutonium. These are the source. These nuclei are so big, they're unstable. They want to break apart, and it releases enormous amounts of energy. Well, that energy comes out in the form of particles flying out, which hit things and warm things up. So you can actually do these reactions and warm up water so hot it becomes incredibly superheated steam, and the steam can be used to turn turbines, and that creates electricity. So you get this thermoelectric energy source as a result. So the nuclear energy from the fission produces thermo power, heat power, that generates electricity as a result of the steam moving a turbine. And you can do this in other ways with underground reservoirs of hot water to produce steam, both from this as well as from natural underground reservoirs of hot water. I mentioned that there's another type of nuclear power, fusion power. Fusion is what happens in the sun. When I told you about the hydrogen atoms being squeezed together, 4 of them to make one helium atom, that produces even more energy, but we haven't been able to get whole reactors to do this over any appreciable period of time. We've only got them to work for like a fraction of a second. People are still working on that. Anytime you ask people, when will this be ready, they say 20 years, but they've been saying that for the last 50 years, so we really have no idea when it's going to happen for fusion energy. But it will be cleaner. Okay, so dry rock geothermal power. So this is another form of energy. So this is where you're using energy that's already in the earth. So now you're not relying on the sun anymore. The sun produced, the earth was produced soon after the sun was produced, and that energy came from there and heating up the core of the earth. So even down in the earth just a mile or so, it tends to get quite warm. And if you have a crack down there or a hole that you drill down there, it's pretty warm down there. And if you pump water down into this hot, dry rock, the water will heat to steam. The steam will rise up a second hole that's drilled in there. So looking at picture C, the steam, you pump the water down the first hole, the steam rises up the second hole, and it can come up and turn a turbine, which will generate electric power. So now you're not really, the only energy you're putting in is to pump water down. The energy of the steam will just pop itself up on its own, and the heating of the water happens because of the internal temperatures under the earth heating it up. So you don't have to put any energy in there. You're using the geothermal energy that's already present to make the steam, which will turn the turbines, which will make the electricity. And then the water will go up, turn the turbines, cool down, and then you just pump that water back down again and let it heat up again. And this is extremely efficient in theory. People are still working on making these better and better. And obviously this works best in places in the world where there is a lot of geothermal power. Iceland is really one of the leaders in this kind of technology because they have so much volcanic land that the country is built on. So with this, we'll end the unit. Thank you very much.